Okay, I think I'm ready to do this lecture on Zoom. I mean, on Zoom and then broadcast it on YouTube. But I really would have preferred to do this in person. I'm gonna go really technical and babble a bunch, and um, I kind of wish that we were together so that you could just stop me and ask me questions in case I misspeak or something. But please just write your questions on the side and come ask me after. You can even pause and come find me and you can ask me before you keep going. That's also totally fine. Okay, so I want to remind you that we're in nuclear fuel, right? Nuclear fuel being this stuff, which means that there's about 3% 235 around. Of all the atoms around us, imagine that you're at the atomic level, of all the atoms, about 3% is now uranium 235. And remember that 236 is inherently unstable. That's not possible on Earth. That nucleus will fall apart. And before anything else, I got to tell you a story about my childhood. I'll try to make it fast. I swear it's relevant. I swear it's relevant. When I came to the United States, one of my father's co-workers invited us to go see a Dodgers game. And it was a dreadfully boring experience for me. I come from soccer culture where people are running all the time. And I went to go watch a game that was essentially what do they call it? Like a no-hitter, almost a no-hitter. Like it had a few people hitting the ball and getting on first or something, but there was almost no score. I believe the end of the game was 0-1. I think that they played another team that wasn't especially good. Anyway, I was just bored to tears. We were up in the nosebleed section. The sun was hitting me in the face. My dad was shocked that you had to pay like whatever, $8 for water. And so basically I just spent a whole day like waiting in the parking lot and then waiting in the bottom of the stadium and then walking up to infinity and watching this game where I didn't understand anything. And it was just kind of dreadful. And I was walking out and like at the back, pretty much like one of the last people leaving. As I was taking a step, $100 bill fluttered under my foot. And you can maybe imagine, um, as a third grader, to find $100 bill. We were poor, we were freshly immigrated. So $100 today would be exciting, but as a third grader in 1984, to find $100, that was a lot of money. I had never considered that amount of money in my life. And obviously the Dodger game became much more memorable after this. And then, like 2 days later, I won a contest where you would mail in Kool-Aid envelopes. Kool-Aid is a powder that you add to water to make it really sugary. It's like a sugary drink. And the little envelopes that it comes in, on the back, it said mail in for a chance to win $100 gift certificate at Toys R Us. And I mailed that in and I won. So I had been to a Dodger game on a Saturday or Sunday or something, and then on a Tuesday or Wednesday, I got $100 gift certificate in the mail to Toys R Us. And I was like, I love America. I love everything. I'd been like really sad and depressed. Our whole family was depressed. Coming to the US was very difficult. We had a really rich family life in Argentina, and we were all alone in a really dangerous part of Los Angeles. So I got to tell you the story. I'm sorry. I take my $200, I go to Toys R Us, I do all the math, and I bought as many Legos as I possibly could. All these castle kits. And then I went home and I just started building Lego castles, and I built this huge Lego castle that was right on the nightstand between my bed and my brother's bed. And we lived in a really dangerous neighborhood, and at night there would be like shootings and people fighting and people yelling and like car crashes and like choppers. And so at night we would often wake up, and when my brother would wake up, he would be really afraid, and he would get out of bed and he'd throw his pillow and he'd run to my mom and dad's room. And when he did that, he would always knock over my castle. rooms were right next to, I mean, our beds were right next to each other. And his pillow, when he got out of bed, you know, he'd cover his head with his pillow. We both would. And when he'd wake up in the morning, he would like throw that pillow off in my castle. Every morning I'd wake up and be like, oh, Juan, you broke my castle again. And I started to notice when I put it back together that the castle had like these average weaknesses where it would usually break somewhere over the drawbridge. It would break, so there'd usually be the left side and the right side, and like there was these little flags that went up on top of the castle. Those would always fall off, and on average it was like the left and the right. Sometimes the thing over the drawbridge would be, the parapet would be on the right side, and sometimes it would be on the left side. But it was basically, it would break in like a left half, a right half, some flags. Because there's like these basic structural weaknesses in my Lego castle. Maybe you can see where I'm going with this. That whenever you break a Lego castle, it has these average breaking points and some little pieces that always fall off. Maybe now you understand why I just wasted 5 minutes with that story. If you want me to try to explain the physics of this, we could, but that literally would take a year or two. So you'll have to forgive my stupid story. We're going to come back to my castle that would always break in the same places. But first I got to switch to my iPad. Hopefully it won't take too long. All right. There you have uranium-235. We're ready to do the nuclear reaction. We're going to split an atom. And uranium-235 is slightly radioactive. It might occasionally shed a piece here or there. But if you have enough of it around, when you throw a neutron, it might stick. Throwing a neutron is actually simpler than you might think. You just take something which is radioactive, that's unstable, and you just put it close to the fuel rod, and because it's unstable, it'll just start spitting neutrons until one neutron goes pop and joins uranium-236. Sorry, 235. And that gives you uranium-236. That is inherently unstable. That's what my asterisk means. So if you have uranium-235 and you add a neutron, you get uranium-236, right? One heavier. We've added one atomic mass unit, one little part. And uranium-236 is unstable. It's going to go POWY. And it's going to break. Now, like a Lego castle, uranium-236 has inherent weaknesses. And so it's going to split into a decay product. We'll come back to that. And another decay product. If we were talking about Lego castles, you could call these the left and the right halves, for example. See what I did there? Because a uranium-236 could split a bunch of different ways. But on average, it'll have one chunk and another chunk. And like those little flags, there will always be a few extra neutrons, 2 or 3. I need you to keep an eye on those. There will also be lots and lots and lots of energy that has no place to go, so it becomes heat. I mean, a lot of heat, like a whole lot. This process takes teeny little fractions of a second. It's really fast, milliseconds or less. Once you throw the neutron, the uranium-235 becomes bigger, 236, that can't hold together. And when the uranium-236 splits, you'll get a left side and a right side, a couple of decay products, and you're going to get some little pieces, neutrons, and you're going to get some heat. That's a nuclear fission reaction. You take 235, which is the fuel, you add a neutron, it becomes 236, which is unstable. That'll split into a couple smaller atoms and a bunch of neutrons, and that'll also give off a whole lot of heat. That's actually the only thing that I needed my iPad for. So I'm going to put away my iPad. You may want a picture of this if you haven't already written it down. And I want to just make sure that I just want to make sure that I hit the right parts in that video. Uranium-235 is the fuel. Neutron is thrown in. That's like a spark that starts the reaction. 236 splits immediately. You get average decay products, some loose neutrons, and lots of heat. I think I just said that. And I want to talk about those average decay products really quick. They're really gnarly. You can see that that has 2 asteroids, meaning it's even more unstable. Watch this. If you have like a giant semi-truck and it breaks down, could you reassemble that? And, you know, let's just for the sake of imagination, you reassemble that semi-truck into a car and a motorcycle, 2 smaller vehicles, okay? Conceptually, that's important, so let's imagine that was easy. Just go with it. Now, could that car and that motorcycle carry all the cargo that the semi-truck had? And the answer is probably not. I want you to consider that the nuclear decay products, those fission products, are smaller atoms, which are very, 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 very heavy, because all those extra neutrons of the uranium got to go somewhere. I hope that makes sense. The decay products have way too many little parts. You see, uranium is really big. It's got all these nooks and crannies where you could stuff a neutron. Just like a semi-truck has all these little places where you could fit cargo. If you try to pack all that extra matter onto smaller atoms, they don't have the nooks and crannies. There's no stable way for decay products to hold all of their neutrons. So the decay products are going to lose pieces. They're going to lose a lot of pieces, meaning that they're highly radioactive. And let's remember that some of that stuff is neutrons, which are sparks, right? Here's the 2 most common reactions. And you probably want to photograph this or write that down so that you'll remember later. I don't know if you need all the numbers, okay? I don't think that you're going to need all those numbers. But I do think that you should have the products Ba, Kr, Xe, and Sr. Now you can imagine these are really heavy, really, really heavy. Ba usually has like 120 something, I can't remember right now. So this is heavy by like 14 or 15 extra neutrons. That is a lot. That's an isotope, which is not like a +1 or a +2 or a +3 isotope. That's like a +13 isotope. This is like a +20 isotope. That means that they're extremely heavy. These are isotopes that have way too many extra neutrons. See, look at this ratio. Uranium can hold a whole bunch of baggage. It's got a lot of extra neutrons because it's a big old atom. So it's got a bunch of little places where it can hold them. But when we try to split that up, there's no place to put it. So lots and lots of neutrons will come out of this. One last thing, I want to remind you that there are many possible products. Explaining this graph would take like about a year of classes at the university level, so let's not explain it, but let's just see what it says. That a bunch of different mass numbers could result from splitting uranium, but the ones that are most common, the highest percentage, are something around SR and something around XE. Those are the averages. These are going to be very heavy. And so we say that spent fuel is the most radioactive thing. Uranium's a little radioactive, but after you've used it to give off that heat, you're left with smaller atoms that are extremely unstable. So they have these predictable, continuous decay. They lose protons, they lose neutrons, they give off tons of heat and tons of energy. Once you start, you have this destable product that's going to keep going, and that's going to keep going, and that's going to keep going. Okay? So by the end, you're left with what's called spent fuel, meaning it has less uranium-235. A lot of those atoms have split. They're not 235 anymore. They're gone, and they've been replaced with those fission products, which are the highest level radioactive waste. We start with something that's a little radioactive, and we make it into the most radioactive thing. That is one of the key issues with nuclear power. So I've spent a lot of time talking about this because you have to understand that there's this like random but averaged product which is highly radioactive. I feel pretty good about that. All right, so let's go back to that reaction really quick. Okay, you have here uranium-235, you have your neutron, you've made it into 236, and you're going to get some spare neutrons, and you're going to get some average products. Okay, different reactors, different temperatures, different types of fuel, give you different averages. Okay, this was one reaction, right? It started with that one spark. But I want to remind you that nuclear fuel is 3% uranium-235. So when you throw one neutron, it'll find eventually a 235. That'll make one reaction. But now we've made more neutrons. And you know, there's probably other 235 around. So once you start this reaction, let's see if you can follow with me. Once you start one reaction, you're going to get some decay products, and then you're going to get some neutrons that will make other reactions, make more decay products, and more neutrons that make more reactions, more decay products. And look, we're throwing off neutrons in all directions now. What's scary about the nuclear reactor is that once you start one reaction, the product will start other reactions. And this is what we call a chain reaction, the nuclear chain reaction. I've got a visual for you. Maybe this would work. Imagine that my man cave, where I am now, was packed wall to wall with those little cheap Chinese New Year's firecrackers. They're like really small. So I take a whole bunch of those little firecrackers and I pack my whole room. Okay, firecrackers. That's a nuclear fuel. And then somebody walking by my man cave throws in a lit match. If that lands on a fuse, and chances are it would because this room is full of firecrackers, right? If you bring in one match, that's going to go pop, and that'll blow up one firecracker. But that one firecracker is going to shoot some sparks, which will hit a few more fuses, which will go pop, pop, pop. And each of those will give off sparks that will land on more fuses, and I goes pop, 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 pop. And pretty soon, we have boom, 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 blow the roof off, blow the walls off, blow up my poor neighbor Imelda's house. The very scary thing about the nuclear reaction that happens inside a nuclear reactor core is that once you start the party with one neutron, you're going to get a whole bunch more neutrons flying around. That's what we call a chain reaction. Remember that this also gives off a lot of heat. So you can imagine that the heat given off starts to escalate. One reaction worth of heat, followed by 3 reactions worth of heat, followed by 8 or 9 reactions worth of heat, followed by 25 or 30 reactions worth of heat, and you're getting hotter and hotter and hotter and hotter until that heat has no place to go and everything starts to melt. That's called a meltdown. By the way, if you want to think of something super scary, this all occurred in 3% fuel. So you can imagine if you had 99% fuel, this all happens in a split second, right? So you throw one neutron into pure fuel and it would go, right? The reaction would accelerate more quickly because there's more uranium-235 around. And so the amount of heat buildup that you get all at once, that's a nuclear bomb. The concussion comes from the expansion of the air trying to take all that heat, and all that heat has no place to go. So it just pushes into the ground and makes the bomb crater, and then it reflects upward into the air, and that's the mushroom cloud. That's a nuclear bomb. But we're not in a nuclear bomb. We're in nuclear fuel. We're in a nuclear reactor. The percentages are lower, so it's not as fast, okay? There's 2 things we got to do to avoid this disaster. We have to control the neutrons. That would let us regulate how many reactions, right? If you could block those sparks, you wouldn't light all the firecrackers. So we have to control the neutrons. That's going to be problem number 1. And then we have to move the heat away. That's going to be problem number 2. And I'm going to take a pause in a minute, but I need you to realize chain reaction and meltdown, what they are. I need you to know the difference between a nuclear reactor and a bomb. And I need you to remember the 2 problems that we have to control. Controlling neutrons and moving the heat away. Okay, so we got the heat part. Now all we got to do is keep that heat under control, and we could boil some water to spin a turbine, right? So we're going to come back in a minute, and we're going to build a nuclear power plant. This is going pretty smooth. I hope you have questions.